Nice to meet you. My name is Charlotte Durand, as Dominic introduced me. I'm just finishing my first year PhD this week, and I'm working in Paris with Tobias Alfonfaci and Marc Bocquet under the direction of Alberto Garassi inside the work package 4 of the SASI project that Chris introduced you at the beginning of the afternoon. And so far, the work that I did is some ML-based emulators of CIS models. So I don't really know the global knowledge of everybody on deep learning, so I will do some deep learning introduction, and then I will basically talk about what I've done so far, so the workflow, some preliminary results, and I will go to the next steps of what I will do for the next 2 years at least. So basically the goal of what I want to do is to see if we can use some neural networks to predict some models. So in this case, I'm working on the CIS model that Sept is developing. It is called NextSim. CIS models are quite complex. We have some multifactoriality. We have a lot of stochasticity. We have some anisotropy, and to add above all of those properties of CIS, we have access to a high resolution model, so we have access to data that are really large, which is also something that we have to take into account when we are building some deep learning models. And as simulations of physical models are really expensive in terms of computational cost, we want to know if we can build a surrogate model based only on neural network that can predict correctly the CIS dynamic, and so that can be quite cost efficient and time efficient also. So first of all, what is deep learning? It's kind of a black box. You have some inputs, you have your neural network, and then you have your outputs. But there is a lot of things that are actually happening in our neural network. Inside this black box, you have a lot of nodes that are stuck on different layers that you don't easily have access to. And all of those nodes in those layers are interconnected to each other. So if we take one node, for example, it will be connected to some nodes on the previous layers. And we're going to get for those connections some weights. And we're going to sum all of those different pixels. And what is really cool about neural networks is that you're going to add some nonlinear activation function, and you're going to have this nonlinearity thing, properties that is really interesting in deep learning, and give access to a lot of max results. So, what have I done? Okay. So I explained how you go in one pass over your neural network, and so at the end, you have your input, you go through your neural network, and you have some outputs, but the goal is to train your neural network. So you have to get a loss that you want to minimize. So I'm, in my case, in a supervised setting. It means that I have access to what I want to have as an output. Sorry. So I have the truths that I want. So if I want to build a loss, I just need to compute the error that my neural network is doing. So for example, just a nice mean square error. And if I compute the gradient of this loss in regard to the parameters of my neural network, I can I can give to my neural network the new weights you need to apply to the different layers to improve the neural network. So that's basically what we are doing when we are training some neural networks. So this is some kind of easy summary of the structure of a deep learning training. We have our input at the beginning, and we are going to go through the different layers of the neural networks, and we're going to get some predictions, so y prime in this case. And we're going to compare the prediction of our models to the true target, and we're going to get, so to the loss function, a score, that will go through the optimizer and which will give us the update on the weights that we need to apply to change the weights of all layers, and we need to cycle it and do it again, and we normally get to train our neural networks. That's the theory. So I have explained shortly what deep learning is, and now I will talk about what I'm actually working on. So the data that I have is so the next thing, the model that is developed by mainly SASIC team. It is a series model that is currently coupled with NEMO, which is an inertial model. We have a lot of data available. I choose to have 8 years of simulation as the input of my neural network, 1 year for the validation data and 1 year for the test data. And what I want to have as the input and the output of my neural networks. So for the input, I'm only working at the moment with the CI thickness, and for the input, yes, and for the output, I wanted to know if I can get the dynamics of the CI thickness. So basically, I'm computing the difference between the CI thickness at time plus 12 hours minus the CI thickness at the time of the input. So what I do ask my neural network to do is to predict the dynamic of the CI thickness at t plus 12 hours. So I did some trials, and of course it wasn't working. So I had to give to my neural networks more information, because it couldn't predict the CI thickness if you only give them the CI thickness. So I actually add the forcings. So I just got my forcings from Euro 5, and at the moment I have just some air forcing, so the 2-meter temperature, the sea-surface temperature, and the velocity, 10-meter velocity. So that's basically my data that I give as input to my neural network. So now the next point is which kind of neural networks are we actually going to use for the architecture of the neural network. As you can see, I'm working with image. So it was quite logical to go into convolutional neural networks, because they're space invariant and they're really used generally in computer vision to analyze images. Because my goal is to learn some patterns, for example, the cracks of the sea ice. And also something that is really important is the marginal ice zone. So that's the limit between the sea and the ice. And I have a lot of mistakes in this zone, which is quite logical. So convolutional neural networks are just some networks that, so it defines how we're going to relay the layer to the previous layer, and you have, if you look at 1 pixel, it's going to have access to only a few pixels around it, and you're going to move this convolutional window over all your image, and you're going to share the weight. So you have not so much weight associated to the layer, and it's really quick to train. We could not imagine doing some dense layers, obviously, to such big images. It would have been way too long, and we don't necessarily want to, for 1 pixel, to get access to the information that are too far away. But it cannot be as easy as this, because in my image, I have a lot of length, so I have a lot of data that I don't want to take care about. So what I did, I used partial convolution. This idea came from a team, so Liu et al. In 2018. And basically what I say is that if we are on the Earth, I apply a mask that has a value of 0, and if I am in the sea or in the ice, or I do have data, I apply a mask of 1. And when I do my convolution, I'm going to multiply element-wise my input by this mask. And I'm going just to get access to the sea and ice values. But of course, if I do this, and when I do the sum, I'm going to have a lot of 0. And so when you average it, you're going to lose you're going to undervalue the actual value. So you have to overcompensate it by doing the equation above it. You have to multiply it by the ratio between the number of pixels in the convolutional window and the number of actually active pixels. So this is really useful in my case. So for the actual neural network structure, I selected at the moment two big ones. The first one is the UNet. So it comes from a really famous publication in 2015. It is kind of logical to use it in CIs because it does. So what you actually do is that you reduce the size of your image, and so you do some max pooling, and then you go back to the original scale, the original size of the image. And this is something that is logical to use in CIs models because we know that CIs is multi-scale. So that's what we wanted to use it. Furthermore, it is really quick to train. And what is nice about being quick is that I was actually capable of adding several time steps for my inputs. So I could increase the number of features that I add in my inputs dataset. The other one is the residual network. So that's just a simple convolutional network where you do add some shortcuts. So you just save your data, your layer at some point, and you add it after doing some convolution. It was too difficult to train at the beginning, so I had to use the fix-up initialization method. So this is just something about the weight initialization, and it is kind of working, but not so much. So I will talk about UNet actually after that. So what I talked about was defining the neural network and training the neural network. But this is not actually what we want to do. What we want to do is to build a surrogate model. So let's say I did train my neural networks. I have my model. I can use it. But now I want to know if I can predict more than 12 hours of dynamic. So this means that I'm going to put the outputs of my neural networks as the input of a new iterations of the neural networks, and I'm going to accumulate the error of my neural networks. And this is exactly what is the goal of my first year of the PhD. So in this case, you predict the dynamics at time t+1. You just have to renormalize it so to get the same structure as the input, and you're going to predict the dynamics at time t+2. So this is what I'm going to show you next. So the big figure on the right is the spatial correlation of my surrogate model at the moment. So the closer to one, the better is it. And the goal is to beat the persistence. So the persistence is just that you say, okay, I keep the CS thickness as the same as my initial state. What you see for the moment is that for my ResNet, I actually almost do not beat the persistence, so I do not affect the CIs at all. On the contrary, for my UNet, I do increase my spatial correlation and actually get some really nice results that you will see afterwards in the video. So let's talk about the blue and the green lines, because this is quite interesting. For the blue line, I actually have only one time step as the inputs. It means that I only have the T, just the CS thickness at time T, to predict the CS thickness at time t+1. And it actually gives better result for the surrogate model than if I put 2 time step as input to predict the t+1 prediction. So this is something we are actually currently investigating, because we don't really understand why. It should be the contrary, actually. So basically, it means that, and what you see on the left is my training and my validation loss. And you see that the loss for the one-time step is actually far worse than the other loss. So we could have expected, say, this loss, and the spatial correlation for several time steps would be much better than one for one time step. So this is what we're trying to understand right now. But to finish my presentation, I just wanted to show you a video. So on the left is the truth, so the actual output of the simulation, and on the right is the surrogate model. So every month I restart, otherwise I would have too much missing. But you can see that I actually have a really good advection of the CIs. And so when the number of iterations of the surrogate model increase, you see that we have some diffusion, which is expected because I have some mistakes. I have some cumulative error that I need to take into account. But we're still quite happy at the moment about the results. So no, the goal is to fight this diffusion process, and the solution that we want to investigate is to add some stochasticity. And so, yeah, we will certainly dig into some generative models. That's the next big point. And for smaller steps, maybe instead of just predicting the CI thickness, going into multivariate prediction. So, for example, we can add the damage as an input and see if the training is easier or more difficult, if it does help the prediction. So thank you for your attention, and if you have any questions.
Your partial convolution, do you only apply that to the first layer?
Every layer.
For every layer?
Yeah.
So have you downscaled the mask?
I downscaled the mask, and I still apply the partial convolution.
Did you try it without, just for the first?
I did a long time ago, and actually my neural network wasn't as good as before, so the partial convolution did increase the training, but a little bit. I mean, it's not a huge difference. So I actually keep it, it's more for the physical sense than just the figures.
That was a nice talk, thank you. So you've trained your parameterization on the last decade of data or so.
Yeah.
But this is looking at a change in climate. So as climate change accelerates, there's a possibility that the extent of sea ice changes and physical mechanisms change. How confident can you be that your parameterizations will remain valid into this changing scene, and how might you account for that?
That's a really good question. For the moment, we have absolutely no insight about this. I think that first of all, we would need to be certain about, really finding the best neural network. And actually, the final goal of my PhD isn't fully data-driven surrogate models. It's more like error correction of the CIs models. So instead of fully predicting the CIs, our goal will be to add just a little module that can do a little bit of error corrections with some observations. And so, if the observation actually, you have some, higher temperature or less C, normally it would correct the model at this time. But you can't have any proof at the moment.
Okay, so I think we should take the rest of the questions offline, but thanks very much, Charlotte.